Hello everyone, welcome back to a new episode of Advent of Code. Today we're going to tackle day 6. I had a little peek at this one while I was getting ready. I just woke up from a nap, so I'm refreshed and ready, and while I was getting ready I had a look. It should be, I think, a relatively short episode. This one takes 3 hours. I just couldn't live with myself. Universal Orbit Map. You've landed at the Universal Orbit Map facility on Mercury. Because navigation in space often involves transferring between orbits, the orbit maps here are useful for finding efficient routes between, for example, you and Santa. You download a map of the local orbits, which is your puzzle input. Except for the Universal Center of Mass designated COM, every orbit in space is in orbit around exactly one other object. An orbit looks roughly like this. So here B is orbiting around A, and okay, fine. In the map data, the orbital relation is written AAA being orbited by BBB. Before you use your map data to plot a course, you need to make sure it wasn't corrupted during the download. To verify maps, the Universal Orbit Map Facility has orbit count checksums. The total number of direct orbits and indirect orbits. So if A orbits B and B orbits C, then A indirectly orbits C. So we kind of have like, number of reachable parents in the tree, kind of, right? And they have a graph here, right? It's a tree, the universal center of mass, branching points where like E and I both orbit D. Fine. Wait, what? L directly orbits K and indirectly orbits all these. I guess it's just kind of weird. I understand the concept. This is a weird example because they give you like a 3 and then a 7 and say, oh, the answer is 42. I'm like, what? I thought they would explain how you get to the 42. But it's relatively simple, right? The most obvious way to think of this problem is like for each node in the tree, how many parents does it have? Right? But that's kind of expensive to compute in a way. It would be sort of nice to because you end up duplicating work, right? You ask L like how many parents do you have, and it's like you have to either like find all the leaves and then you can reuse computations. Like L will ask K how many parents do you have, and then we'll only use that once. Because in a way, what am I saying? I don't know. But it seems like a good start is just like build this structure and then traverse it recursively with, I suppose, a catamorphism starting at the root. The other thing you could do is not build this structure like as an actual object graph, but as a map where like each key just points to its parent, and there's no child stuff tracked at all. That would be relatively simple. The other thing is you could probably get like for part 1, you could get away with not actually storing this graph at all, I think. Right? Whenever, like, let's look at the input here. Are things always, I guess it's hard to tell if they're in order, right? Well, they must not be, actually, because COM isn't first. Right, there's only one thing orbiting COM, which is SNP. But that's not the first thing listed. So if we look for SNP, it's here twice. And it's hard to tell, like, I mean, I don't know. As it happens, one of them is fairly close to COM in the list and the other isn't. I don't know. So the number of lines in this is actually very large. There are a lot of orbits. And if we don't do something to reuse to save partial data, I think this will like take a very long time. When he builds things with this kind of graph, he tries to make sure that it's expensive to do it wrong, I think. So I think that we should just actually build the tree and then traverse it, and it'll be totally lovely. It's a little bit hard to do that if the well, no, I guess it's not. We'll be maintaining a tree, right? And each node in the tree kind of has to be a map, right? Map from like name of node to the node itself. I don't know, that kind of sucks, doesn't it? Because you still have to have a way to find the map for a given node when you're updating it. So you need like a global map. This like reminds me very much of something I did in the previous year, and I did it in a cool way with like tying the knot on a like self-referential map object, and it was great. And I think that same thing can apply here, but I'm just not quite seeing it. I don't quite understand the total amount. Okay, so maybe what I should do is just start like drawing up some types and like seeing what it is exactly that I need. So like we have like a data orbit, right? It's not really an object, it's a mass that has things in orbit. It's a mass with a string name and I mean, it could just have a list of children. They don't have to be a map, necessarily. I imagine there are relatively few children, and we probably don't even need to look them up by name that often. But, like, I mean, why not have a map, right? Oh, well, if the masses have named pointers to their children, why do their children have names at all? You can figure out your name by like the link that was followed to get to you, right? Seems to me. Okay, and the other thing is we should definitely make this a polymorphic type so it can store some data. That'll be useful somehow. Maybe we'll want to store the total number of children or whatever. Yeah, so something like this is what I was thinking. And not map. That's already a named thing. What do they call these in the problem? They call it an orbit map, which, like, I don't know, whatever. A map from string to mass of A. So this is kind of like our goal, is to compute one of these and then recursively consume it. And we probably want, well, okay, let's just import like everything in parsec. Oh, except like I don't even remember what the thing parsec modules are. Like there's parsec char, and then there's like regular old parsec, char, string, and then there's there's just like text parsec. So parsec has like most of the combinators that you would want, and the parser type and so on. Commonly used character parsers. Okay, so parsec string has like the parser for strings, or the parser that consumes strings as inputs. Char has simple parsers for characters. I don't know. Maybe like parsec is it's just like more than I really need, but it's so nice. And in string, yeah, char. Okay, yeah, we're gonna need like one of and none of and stuff like that in char. Okay. I don't know. Parsec's kind of silly, isn't it? We can just like split on lines and then split on parentheses and then we're done. Yeah, forget parsec. Okay, so let's write parse is a function from string to pair of string and string, and parse is yeah, break, I guess. So we'll actually, you know, I can just say let a be is that about right? So if I here say parse yeah. All right. So prepare is just like lines, and our input is a list of pair of strings. Map parse. Okay. And what we have to do, I don't know. Maybe that shouldn't be our input. Maybe we should, yeah. Our input will be like having built the map, right? So okay, mass has a string name, but its children don't. So add, I guess, is a function from orbit map A and an A to no, and a mass of A no, and two strings. Okay. Right, so the idea being we're going to look the thing up and just put it in there with no data. I don't know, I guess I might as well, like, in case there's somehow some data that I have, even at construction time, I might as well put it in there, right? So add m v center outer equals okay, so now in map there's some insert function that does exactly what I want, probably insert with data map lazy. Insert with combines new and old value. It inserts the pair key value if the thing doesn't exist, and if it does, then it calls F to combine them. That's not quite like the easiest thing. Update a value, delete a value, alter. Got it. So alter is like a very general function, which is sort of what I want. You could certainly do it with like insert with, but then it's kind of weird because you're building an entry and then you might not add it. You might decide to just concat it to the existing entry, right? So I think I like alter instead. Okay, so m.alter at center. No, it wants the function first. Combine center m, and then that's all it wants, and we have to define combine of nothing. Oh, I bet we can do like a maybe here instead. We'll do that in a second. Now we need to build the new mass. So we'll say it's a mass center containing only well, I see. The problem here is that we want to add a path from a child to a parent, and either the child or the parent might be absent, or both, but not neither. They can't both already be there. Okay. And for each one, and they need to both be there after this, right? Maybe it would be way easier if we didn't try to build this data structure all in one go, and if we just had a map where everything pointed to its parent. Then what? Then you have to it's still kind of hard to do the final computation that we want if we just have pointers to parents. So you have to turn that into something richer somehow. Just like labeling each node with its depth from the top of the tree would be fine. But that's not so easy either. Why is this so hard? So something that I did in last year's problem. That was about like weights, wasn't it? There's a tree of things balancing on each other. Something I did in last year's problem was to assume that the parent is already in the tree. And if it isn't, it kind of gets resolved by tying the knot. But I don't know how to do that here. Maybe I've just sort of lost touch. Okay, well, I'm a little bit stuck on this idea, and so I'm going to just do something simpler that I know I can do. And maybe we'll get back to the actual tree later. In fact, let's leave these types here. But type parent map, I guess, of A is a map from string to pair of string and A, where string is the parent. Right? And so now a parent map of A is just like this is trivially simple, right? We know that the node, the outer node, has never been added before because it can't orbit two things. So we can just say m.insert. What order does insert take its friggin' arguments? Right, it takes the key first, which here is outer, and then the value, which is center and V, and then M. Okay. So that at least is easy to do. Although, like, do we really need to do it this way? Couldn't we just use, like, from list, basically? Add all is a function from list of pairs of strings to parent map of nothing. Add all masses equals m.fromList center outer masses, then just outer pure outer center nothing. Yeah, so I guess our input can be then a parent map of nothing. Come on, cursor, get over here. I want a capital M. And we can just throw an add all in here. Oh, I made it a list of parent maps, not just a single parent map. Yeah, so now we could do something like prepare of com B and a, I don't know, BA, I guess, right? And it says, oh, okay, A has B for a parent and B has com for a parent. So I guess what we need then is just a function that turns a parent map of nothing into a parent map of int, right? And the center of mass orbits nothing. So that it's fine that is like, because there's something sort of weird here. The center of mass is not a key in our map, but that's fine. We don't need to know how many orbits the center of mass has. We know that number is 0. So maybe here's where we can do that knot tying I was talking about. Concentric orbits, or indirect orbits, I don't know, is a function from parent map of A, where we're just going to ignore the data, to parent map of int. And concentric, I'm going to cheat, by the way, and actually do like what sort of counts as some recursion here, of m equals t, where, so t is going to be a map whose values reference the map t itself, where t equals can I just fmap? What exactly is it that I want here? When I get right, the problem is it's hard to start with just the leaves this way, right? Well, here's a thought. If I just flip the map that I have, right? So that com points to the list B and B points to the list A, then we actually have a single structure with a proper root. So, and from that, it would be pretty easy to do, I think, the recursive, oops, orbit thingy, right? So I don't actually want this. I want a function like invert, right? Function from parent map of A, again, I'm ignoring it, to orbit map of int, right? I think. Well, orbit map of, let's say, unit, and then I'll do a second pass over it to convert, to do the counting. Here I just want to flip the tree around. So invert of m is m dot from list with wait, shouldn't this be a oh, I made this a map from a string to map. It would be kind of nicer to have just to build just a mass of A, wouldn't it? Okay, let's why is this so hard? This is a simple problem, and I'm just like, I don't quite get what I'm doing. what is it that I want as a result of this? All I need is like a rose tree, basically, right? I don't even care about the names of things, although really I should keep it. So I guess maybe what I should do is, as another intermediate step, and I hate that I keep breaking things up like this for no good reason, build like yeah, I guess just a map where the key is the node being orbited and the value is a list of names of nodes orbiting. Okay, so it's like this is an we're not storing anything else here. Fine. Okay, and from list with takes a combining function, that's append, and then a list of things. Actually, this is going to be a very simple thing, isn't it? We're just going to say pure of vk like this. Oh, right. Our soaks here, we have a parent map, which means we have a parent map of A. So the value is a string and an A, and we just don't even need it. So if we then go back to our example here and like let's put in an actual recursive or like something being orbited twice, right? Com C, like so, right? We have this, and if we say invert that, we say com has C and B has A, right? And that's basically exactly what we need as a result. From there, it should be, I think, pretty easy to yeah, it should be easy to compute the weights. We start with center of mass and say the number of orbits of a node is the number of children that it has plus the number of orbits that each child has. Okay, so indirect orbits is a function from m.map of string and string to we could just compute total weight, but I feel like I might, well, I think that's actually fine. We'll make that like be part one, basically. Yeah, and let's make that, this type is actually our input. This is like really useful. This whole parent map thing sucks. And so does orbit map. So part one of M equals total orbits of M of actually just center of mass, where total orbits of K equals case lookup wants a key first, so km of nothing 0, and otherwise just children to be one plus total orbits k for each k in children. Let's say C here to not be confused with the k in the outer scope. Right, so the idea is each child has some number of orbits. Oh, is it just 1 plus this? Is that right? I don't think it is. Because if there's some, it might be like 2 times the total orbits or something, but there has to be a 1 added somehow as well. If like A is orbiting the center of mass, and A has 5 total descendants, right? Then the fact that A is ordering the center of mass, how many orbits does that add to the universe? It adds, well, each of its descendants is now orbiting 1 more thing, and A itself is also orbiting 1 more thing. So actually this looks right. 1 plus the total orbits that were already there. Okay, I mean, I guess let's try it. File doesn't exist. Well, you got me there. $17.27. All right, it's a number. I'll take it. It's not the right answer. Okay. So let's try our little example here. I feel like we should, oh, hang on. I feel like we should be able to parameterize our like go. Oh, everything's named go. I don't know. I can't call this go. I just can't bear to have a top level binding named go. Handle is a function from string to IOU, right? And handle s equals read file of s. Main equals handle of input.txt. So this way we can say test input.txt. And now we can play with this a bit. So what if main was to handle test input.txt, right? Like, what answer do we get? Oh, I called it text input. All right, whatever. 11. So that's hugely wrong. Did I just count the number of nodes that exist? I did. That's weird. So what should happen here? When we get to the center of mass, we should compute the total number of orbits for just the system B. Well, let's try some really friggin' simple inputs, right? Like, I don't need this. Okay, let's try like, we were using this before, right? So let's try part 1. Like, what do we get? We get 3. Is that right? A orbits the center of mass. No, sorry. B orbits the center of mass. That's 1. A orbits B. That's 2. Center of mass orbits... C orbits the center of mass. That's 3. We aren't accounting for the fact that A is orbiting B for some reason. Do we just need to return 1 instead of 0 in the base case where we don't have the thing entered? I'm not sure. Sorry. So we get to the center of mass. Okay, let's just do this one by hand. How many are there supposed to be? I think the answer is 4, but let's just confirm. There's clearly B is around the center of mass. A is around B, and therefore A is also around the center of mass, and C is around the center of mass. So there are 4 total orbits. Why don't we get them all? We start at the center of mass. What the hell is this music? I listen to music while I'm doing this stuff. You guys can't hear it, but this song is just, what the hell? I don't know. I listen, it's like chiptunes kind of stuff, but this one's like a little bit, like just too noisy for me. So, okay, let's have this function in sight, right? Total orbits for the center of mass. And we say total orbits for the center of mass is look up center of mass. And we got back a list. CB. Definitely. Like, here it is. Okay. And for each orbit, C and B, we look up how many orbits that thing has. And we add 1. So how many orbits... So then what we can say is T of com equals 1 plus sum of 1 plus T of C, 1 plus T of B. Fine. Now we need to compute T of C, which is, well, what? We look up in the map C, and we get nothing, right? So we say 0. Very easy. T of B, we look it up in the map, and we get the list A. So we say it's the sum of 1 plus T of A. How about T of A? It's 0. So now we can use this here and say it's sum 1 plus 0. Now for center of mass, maybe I'm supposed to double it? That doesn't feel right. Oh yeah, it does. Because what I've computed here is kind of the number of... Well, no. I'm adding together the direct orbits of a node with the indirect orbits of that node's children and adding 1 to each of those, right? So So where exactly does this go wrong? Which of these values are correct? How many things are orbiting C? 0. I think that's fair. Obviously, C is orbiting 2 things, but that's a different question. Okay, I guess that's why this is the wrong answer, isn't it? I've computed the number of things which are indirectly orbiting the center of mass. But I haven't considered like all of the other indirect orbits, I think. So maybe multiplying by 2 actually is the right idea. That would get us to 4 in this case, because most of these multiplies by 2, the ones for A and C, would do nothing. But the one for B would add exactly 1, right? So that actually seems about right. And if we do this now, we get 4, as I predicted. Okay, so... Oh, that's very nice. A very large negative number. Did it actually overflow? That does not seem like a good idea. That suggests that I'm way off. Yeah, there probably aren't this many. All right. Well, I mean, just for laughs, then. It's 157 here, so it's too large even for that test input. But why, though? It seems like I should be computing a recursive sum of a simple function on this data structure. What's wrong with this picture? Okay, so I now see, I think that using total orbits at all in the recursive call is like sort of wrong, isn't it? Because it makes the forking apply like too much. Right, if a node has 2 children and each of them has 2 children, how many orbits are there in that system? Well, for the root node, there's 2 direct orbits, and for the 2 intermediate nodes, there are each 2 direct orbits, so that's 6. And then for the root node, well, okay. Let's look first at the 2 intermediate nodes. They each have a total orbit count of 2. I'm just thinking it leads to like double counting, basically, if we multiply by 2. They each have 2 orbits. Yeah. Okay. So the problem, I think, is that we're sort of like, maybe it would be simpler to show here. Like, how many orbits are in this JKL sub branch? 1 for L to K, 1 for K to J, 1 for L to J. Actually, let's look, because I think you might need a depth even deeper than 3 to make the problem obvious. So let's look at EJKL. L is around K, that's 1. L is around J, that's 2. L is around E, that's 3. K is around J, that's 1. K is around E, that's 2, plus our 3 is 5. And J is around E, that's 6. So this branch has 6 total children, total orbits. But when we add this branch onto like D, D doesn't gain 6 new indirect orbits. It only gains 4, right? So we need to add the total orbits for E to like D's orbit count. No. Yes, we do need to do that. We're computing the total orbit count, not just like for everything D and below. So we need to add all the total orbits from E to that because they count. But you don't want to double it. We want to add in the total number of descendants that E has, not add another copy of all of its total orbits, which is larger. So it's something like total orbits C plus total nodes C. Total nodes of a K this is just such a brute force way to write it, but I'll think of something clever later. So if the node has no children, there's still one node, right, which is the node itself. Just x's. It is 1 for the node itself plus 1 plus total nodes x for x in x's. Is that right? No, I don't want to add 1 here, just total nodes. Why don't you like my type? Cannot construct. Okay, well, let's tell you the type I thought it was supposed to have. Is string integer. Ah. Yeah. So now we get 42 for the test input, which is what it was supposed to be. Okay. And a fairly plausible number for part 1. It's the right answer. Okay. So the problem was that I was a little bit like too... I didn't think about the fact that there are 2 things that we need to know about each node, right? You can't just know the total number of orbits. You have to also know the total number of children. So that's kind of an interesting little traversal. I am not at all going to try to fix this to not use recursion, by the way. I don't know if I've mentioned some. I'd like to avoid recursion here to like practice using other things, but I clearly don't have the stomach for it. Oh, just git add to everything. Day 6, part 1. Now, you just need to figure out how many orbital transfers you need to take to get to Santa. You start at the object you are orbiting. Your destination is the object SAN is orbiting. An orbital transfer lets you move from any object to an object orbiting or orbited by that object. Ooh, exciting. So... between the objects they are orbiting. Whoa, wait a minute. Really? Move from any object to an... okay. I thought briefly that we could move other objects around somehow. But I think we only move ourselves, and I just was confused by what the map looked like. Is everything else still completely in place? We've just moved you and San. Yeah, okay. So this, I think, is a pretty simple tree operation. And we don't even need the reversed... we don't need the inverted map. We need the original map where leaves point to their parents. Because what we kind of want to do is find the least common ancestor of me and of you and Santa, and additionally count how many nodes it is to that least common ancestor, and then that's just the answer, right? So to move from K to I, we're no longer, so we want to know the number of steps from K to I, basically. So not exactly the number from me to Santa, but from my parent to Santa's parent, which is kind of the same thing as saying from me to Santa, but add 2 or subtract 2 at the end. Both would be fine. And what is a good least common ancestor algorithm exactly? I mean, it should be fine because we could just walk all the way from us up to the root and from Santa up to the root and compute a map of every common ancestor. In fact, compute 2 maps. One that is a map from all of my ancestors to their cost, and one from all of Santa's ancestors to their cost. Intersection them, combining with addition. And then take the smallest value. It's not super efficient. What would be better, I guess, would be to build the common ancestor graph from me up to the root, and then start from Santa searching upward until you get to a node we've seen before in the previous traversal, and then you know you're done. In principle, it seems like maybe you could do better by traversing up 1 from Santa, then up 1 from you, then up 1 so I don't know. I'm not sure that actually turns out to be asymptotically any better anyway. Yeah, so for each node of interest, we compute a path all the way up to the root labeled by cost, intersect the 2, and find the cheapest thing. And I think that's all we have to do. But it does mean that invert was actually not part of our part 1. Whoops. What am I doing? It was kind of like a parent map of unit, right? And we just need to take that invert. basically. Yeah. And we still get the right answer. Yes, very good. So now part 2 can take the map that it actually wants, which is the one from keys, or from nodes to their parents. Well, we'll call it P. That's what we called the other one. It is the minimum of the elements in the intersection. Is it intersection or intersect? Intersection with plus of U and San, where U equals, well, has U has San, like that, where paths of K, case lookup K in M dot lookup K in P of nothing, then there are no further paths. What am I even doing? This path is supposed to be a list. Or a map. Okay, so it's more like m dot from list of costs K, and so if K is not present, then nothing. Just and remind me, I mean, it's just, our map is just a string value is all that's in it, right? In our parent map, string A. Okay, yeah, very funny. Then it is parent. So let's see. The cost to get from K to K should be 0, right? And to get to any parent costs 1 more. So we're like mapping add 1 over the results of looking up all the costs for the parent, right? So why is this M lighting up? Intersection with takes a function and 2 maps. That seems fine. Ambiguous type variable. I haven't told you what the key should be. Isn't it a string? Costs has the wrong type? Oh, I have a list of tuples. So I don't just have a list. I have to like... There we go. So for each tuple in the list, we fmap successor into the second part of the tuple, which is what fmap does for tuples, adding 1 to the total cost. So what's wrong up here now? Okay, well, here's the thing. Costs, tell me what type you think costs has. So costs is a function from string to map m.map from string to int. Okay. That was part of the problem. Maybe you had a weird idea about the type there. No, costs is not that. That's what that's the type paths has. Right? Oh, was that all you needed? You're happy with the types now? That's interesting. What was ambiguous here? You didn't know what kind of number to use. I just said 0. Interesting. No, but you should have known, right? Because of this. That is weird. Okay, I mean, let's try it though. 547. So we got a number. That's pretty cool. But before I put it in, like, do I think it's right? Did I get the boundary conditions correct? We're starting with U, and boy, how many lines are in this file? I don't remember. XL, there we go. 1727. Okay, so it's totally plausible that you could need like 500 steps, right? A little surprising, but plausible. So that's to move from U. So we need to subtract 2 from this. Because this is counting how long it would cost to, like, how many links there are between you and Santa. But we don't want, like, we don't need to climb up from where we are and then down to where Santa is. We just have to orbit where he is. So I think we need, in fact, like this. And now we get a slightly smaller number, 545, which I think is correct. It's not the right answer. It's too low. Interesting that this time he actually says it's too low. On some of the others, he hasn't been. Well, once again, I guess what we should do is try it on the test input, right? Give me back main, and let's run it on... Still got the wrong name. You know, what can you do? 2. 2? Okay, well that's interesting. Maybe I already had the boundary conditions handled correctly, because the number's supposed to be 4. I said it costs 0. I thought I was counting it as being like you need 0 to get from U to U and 1 to get from U to K, and therefore I needed to subtract 1 to count that. But maybe I didn't do it that way? I mean, I'm game. I'll try it. It should return 540. It returns 4 for that test input. It would be kind of cool if it like told you the actual list as well, wouldn't it? So I could confirm that I'm getting it right. But whatever. Let's just hang on. What was the number we put in before? Was it 50? I thought it was 57. Oh, right. I was like all set to type in 54, which is like an answer from the test problem. No, 547. Okay, got it. So we change this back to input.text. And we get 547 again. So let's try that. That is the right answer. Interesting. There you go. So now we're getting the idea that this is like... I was close when I guessed it was like a planet with rings around it. It looks like this is orbits of planets around other planets or something like that. Okay, well this one took like an hour? Over an hour. Way longer than I thought it would. This was like, I thought, a pretty simple problem. Yeah, not too bad as a part 2, I guess. Yeah, definitely, like, I guess need to brush up on my, like, techniques for creating recursive data structures, especially recursive, like, maps. This is the kind of thing that I feel like would have been so easy in Clojure somehow, maybe, but I don't think it actually is. Certainly flipping the map would have been easy, but that was easy in Haskell too, right? It was like figuring out what I actually needed the structure to be in the first place was kind of harder than I would have liked. Why does it not like this type? It actually doesn't mind. I must have changed something when I put the type in, I guess. And that also happened to fix the problem. That's very odd, because I could swear there was an error and when I hadn't touched anything here. Oh, I bet it was because I still had this, right? Yes, and now we get this back, which is I don't know how to add, like, unit is not a number. Okay. Fine. Okay, cool. Well, then I guess we're done for today. Hope you guys enjoyed. Thanks for watching, and I'll see you next time.